So I'm gonna, yeah. Good afternoon, everyone. Welcome to our CIBSE webinar today. We're gonna wait some more minutes so that the rest of the audience can join, and we'll crack on soon. Thank you. Good afternoon, everyone. My name is Alejandro Falcón, CIBSE UAE Social Secretary and Events Organizer. And I welcome you today to our CIBSE UAE webinar, Dehumidification and Drying Psychrometrics. CIBSE's responsibility in the region is to promote the intellectual welfare of its members and improve the understanding of building services, engineering within our society by organizing events and other activities related to the built environment. Today, we're going to show you a speaker introduction, a speaker agenda, note of the session, a speaker presentation, Q&A session, and close out. Our speaker of the day is Julien Taschot, Applications Manager of Condair Global Sales. Julien has been with Condair for 15 years. He has been involved in many projects over this time, covering applications such as data centers, clean rooms, general HVAC, and industrial processes. Offering Condair's wide range of humidity control systems, Julien assists local agents, distributors, consultants, and contractors around the world in selecting the best solution for all applications. Condair is the world leading manufacturer of humidity control products, offering dehumidification, humidification, and evaporative cooling. With its headquarters in Switzerland, the company has production sites in Asia, Europe, and North America, over 750 employees, wholly owned sales and service operation in 22 countries, and international sales partners in more than 50 further regions. The Condair Group is represented in the United Arab Emirates by its sales partner, Handasiya FZ LLC. Julien will walk us today through the following agenda: how desiccant and condensing dehumidifiers work, the drying psychrometrics of desiccant and condensing systems, best practice in dehumidifier selection and installation, how to correctly size a dehumidifier for a project. If you have a question regarding the technical content of the presentation, please write it down on the Q&A panel. You can see a symbol drop down on the top right side of your screen, and your question will be answered by the speaker during the Q&A session. Your camera will be off, your mic will be mute. If you have joined the webinar as anonymous, please make sure you write in the message box your name and surname so that you can receive your CPD certificate after the session. Without further delay, I give way to the speaker of the day, Julien Taschot. Julien, the call is all yours.
Thank you very much for your introduction, Alejandro, and good afternoon, everyone. I will turn my camera off from now on, just so you can really focus on the presentation itself. And then I will happily, after the presentation, try and answer all the questions that you may come up with during the presentation. So let me just turn the camera off and share my screen. I hope you can all have a good visual of my screen. First of all, thank you all very much for joining this webinar, very nicely organized by CIBSE and Alejandro. I'm very grateful for your time. This presentation will last approximately 45 minutes. And then we will follow this up with the Q&A session as indicated by Alejandro. So without further ado, let's start by having a look at the agenda and what are we going to talk about today. So first of all, we'll have a look at applications and where dehumidification and generally humidity control may be required. What kind of areas, what kind of industries may need humidity control. Then we'll have a look at the different dehumidification principles and how they fit into the psychrometric chart. Then we'll take a view on the different products available on the market and what kinds of features and characteristics each product presents. And then we'll have a look at sizing and selecting the right dehumidification solution for your application. And we'll finally round this presentation up with a comparison between the technologies through a list of salient points, main differences between the technologies that we are going to talk about. So, first things first, applications. There are hundreds of applications that do require humidity control, whether it's humidification or dehumidification. Obviously, this is only a 45 minutes long presentation, so it would be way too long to list all of them. But effectively, we tend to separate applications between process applications, such as those listed on this slide. And process applications are typically industrial processes where we are dealing with hygroscopic materials. So in other words, the quality and the shape of the product will depend on the amount of moisture that it holds. Typically with dehumidification, we, and particularly for some drying processes, such as in the food manufacturing industry, for example, or pharmaceutical industry, the idea of dehumidification in that respect with a hygroscopic material is to try and achieve an ambient moisture content that is slightly below the equilibrium moisture content of the product. So if we think, for example, of I don't know, paper, for example, will have a certain optimum moisture content in the paper itself, and if the ambient relative humidity or ambient moisture content around the paper is above that moisture content, then the paper will tend to absorb moisture. If we go below the relative humidity or below the moisture content, the equilibrium moisture content of the paper, then the paper will start losing moisture and will dry. So the idea here in most process applications, when we talk about dehumidification and drying, is to do with maintaining an ambient relative humidity that is slightly below the equilibrium moisture content of the product that we are dealing with in order to improve drying times and therefore improve productivity. There are also a lot of non-process applications, and non-process applications are again typically to do with like, for example, storage areas, museums, archive stores. They're also a lot to do with maintaining the moisture content of hygroscopic materials that might be stored or that might be exhibited in museums. If you think paintings, wooden instruments, artwork, all those things are again highly hygroscopic materials, and the shape will change depending on the ambient's relative humidity. In this case, however, we're typically not trying to dry the product itself or the artwork itself. What we're trying to do is we're trying to maintain a stable temperature and humidity all year round in order to maintain the balance between the moisture content of the air and the moisture content of the piece of art that we are trying to protect effectively. It's all about protecting the artwork in this case, or the paper integrity. There is a big financial implication actually with museums and art galleries in terms of when they are looking to accommodate high value traveling exhibits that go around the world. They need to prove to their insurance companies that they can maintain a stable temperature and humidity for at least 3 months prior to receiving the traveling exhibit. Failure to do so would result in non-insurance and could have a massive economical impact on, say, its museum or art gallery. So it's a critical aspect of this type of area as well. There are also loads of storage applications, particularly military storage applications, but I'm thinking also energy plants, turbines, where here the idea is to avoid condensation from happening, particularly in energy plants and turbines, where there are usually a lot of pipe work with cold liquid inside. Obviously, what we then try to do with a dehumidifier is to decrease the dew point in the area so it matches the dew point of the pipework and therefore maintains a stable environment without condensation forming on some of the colder surfaces. And there's also a third type of application where dehumidification is very commonly used, and this is swimming pools and spas. Whether they are large Olympic swimming pools or some public hotel swimming pools or even private villa swimming pools, the idea here is to, maintain the relative humidity of the swimming pool around 55 to 60% relative humidity, so as to keep, avoid condensation, of course, but also to keep the water evaporation down to a minimum. Effectively, it's all about maintaining the right balance between the air vapor pressure and the water vapor pressure. But as you can see, obviously, hundreds of applications do require humidity control, whether it's humidification or dehumidification. It is a critical aspect in many areas, many of which I wouldn't have mentioned in this introduction. Now, when we talk about dehumidification, there are different dehumidification principles, and the way different dehumidifiers work can be very different. So in terms of dehumidification, there are two main technologies available to physically remove moisture from the air. We are always talking about either condensing dehumidifiers or desiccant dryers. And as you will see in the next few slides, the principles of operation are very different. Their application is also very different. and their characteristics in terms of installation requirements, power consumption requirements, running costs are all very different. So over the next few slides, I am going to really do my best to introduce both technologies and give you as much information about the main features and characteristics of both those technologies. So without further ado, we'll start with condensing dehumidifiers. Now, I'm sure most of you will recognize this, this schematic as being your typical direct expansion system, cooling system, effectively. So for those of you who are not so familiar, let's just run through the principle quickly. So this is a circuit that is full of refrigerant. So as the refrigerant leaves the compressor, it is at high pressure and high temperature. So as it goes through the condenser coil, which basically acts as a heat exchanger, the temperature of the gas will start decreasing, and it will actually push a lot of heat to after the condenser, effectively. And as the pressure decreases and the gas form starts to cool down, and therefore it changes its state, and when it gets to the top of the condenser, it actually arrives into a very liquid form. It's not fully liquid, but it's very liquid. And then that liquid goes through an expansion valve, and as it goes through the expansion valve, the liquid then comes at a lower pressure and a lower temperature, and then it then goes through the second part of the refrigerant circuit, which is the evaporator. And in there, the heat exchanger coil will basically just do the opposite side, and the liquid will start boiling. It will start absorbing energy from the air to do that boiling cycle, and it will actually leave the evaporator as a mainly gaseous state, ready to go into the compressor again. And then the cycle basically is a closed circuit refrigeration cycle. So in effect, what does it do in terms of dehumidification? What physically happens as air goes through this refrigeration circuit? Well, typically the warm humid air first goes through the evaporator, but because of the cold temperature of the refrigerant at that point, as the air goes through the copper tubes, effectively, it starts cooling the air down, first of all sensibly, and then as the air reaches dew point, it then starts doing some latent cooling as well. And therefore, latent cooling is basically water starts condensing on the evaporator fins and falls down into a condensation tray, which is typically connected to a drain. So as the air goes through the evaporator, it is cooled down. So it comes off the evaporator as cold, dry air. But then what happens is the air then goes through the built-in condenser. And as the condenser does release heat through the refrigeration, through the refrigeration process, it then picks up heat and is supplied as warm, dry air into the space. So, like I said, it's a typical direct expansion system, very similar to what you will see in split air conditioning units, for example. The main difference will be that we are putting we have a built-in condenser, which means that we are putting the warm, dry air back into the space instead of exhausting the heat to outside. So in terms of what that looks like on a psychrometric chart, because I do believe that a psychrometric chart, first of all, is the best tool for sizing and selecting a dehumidifier. But how does the condensing dehumidification work on the psychrometrics? Well, actually, first of all, for those of you who may not be very comfortable with a psychrometric chart, I thought I'd just run through the different details available on the psychrometrics first of all. So as you can see on the bottom axis here, the bottom horizontal axis, we have values here which are basically your dry bulb temperature in degrees Celsius. In other words, the temperature that you can read off of any standard thermometer or hygrometer in a space. On the right hand side, on that vertical axis on the right hand side, you have the moisture content of the air in grams per kilogram. And then the outside curve here is the saturation line, otherwise known as the wet bulb temperature. So it's basically where your air is saturated and physically cannot absorb any more moisture, cannot contain any more moisture. After past that point, it's supersaturated, water starts appearing in liquid form. The internal curves here that we can see at the from the top here, 90, 80, 70 are your percentage relative humidity. Now, relative humidity means that the humidity is relative to a temperature, and it will therefore give you the actual physical moisture content of the air. So, for example, if we consider a temperature of 20 degrees Celsius and a relative humidity of 50% RH, then the diagram will actually give us the amount of moisture in the air at that point, which is around 7.4 grams per kilogram. And 7.4 grams per kilogram is half of the maximum moisture content of the air at 20 degrees C, which is just below 15 grams per kilogram, effectively. So that's what the psychrometric chart gives us. The psychrometric chart also gives us the oblique purple lines on the side here, which are referred to as the specific volume in meters cubed per kilogram. So that's basically how much space does 1 kilogram of air take. So once again, if we want to find out the specific volume of the air at 20 degrees C and 50% relative humidity, we look for the nearest oblique purple line here, which is actually 0.84. So at 20 degrees Celsius and 50% relative humidity, the specific volume of the air is 0.84 of a meters cubed per kilogram. And then finally, we also have on the outside of the psychrometric charts, we have the specific enthalpy scales in kilojoules per kilogram, which is basically the amount of energy in the air at any given point. So once again, if we have room conditions at 20 degrees and 50% relative humidity, to find out how much energy is in the air at those conditions, all you need to do is to draw a line between crossing that point at 2050, and that basically crosses the matching values on the top and the bottom scale of the diagram. And that basically gives you how much energy is in the air at that particular condition. I hope this is clear for everyone. So in terms of condensing dehumidifiers, so if we consider a condensing dehumidifier, what physically happens to the air? What's the process that it follows? So first of all, there will be a cooling component. Like I said, the warm air is drawn usually from the space and is first of all pushed through the evaporator. So it comes in as condition number 1, and then as it goes through the evaporator, it will first of all do some sensible cooling, where the only thing that changes is the temperature. But then, because the surface temperature of the evaporator coil is much lower than dew point, it then starts doing some latent cooling as well. So where basically it does further cooling, further reduction of the dry bulb temperature, but it also starts stripping moisture off the air as well. As you can see, there is a difference between the air off moisture condition and the air on moisture condition. And this is exactly how the condensing dehumidifiers start removing moisture from the air. And then the second part of the process, as we know, it leaves the evaporator as cold dry air, and it then goes through the condenser, and it will always supply as number 4, which is basically always slightly greater temperature than the air on conditions, simply because, as we know, the change of state of the refrigerant means that there is an energy release into the air, which means there is always going to be a slight heat gain into the space. So what does that mean in terms of the changes to the air on the supply side of it? It means there is a moisture differential, which is typically around 4 to 5 grams per kilogram. It really depends on the cooling capacity of the evaporator coil. And there is also an increase in temperature from the air on conditions, and this is typically around 1 to 1.5 degrees C per gram of moisture removed. Those are only indications, it's just to give you a guide. I hope everything is clear on this condensing dehumidifiers and how they operate and what effect does it have on the psychrometric charts. Now let's have a look at desiccant dryers, the other type of technology that's available for dehumidification. And as you can see, this is a completely different principle of operation. So first things first, we always, when we refer to desiccant dryers, there are always 2 air paths to take into consideration. The first one shown at the bottom here is referred to as the process air path, and it usually draws the air from the space or from outside, depends what you're trying to dehumidify. It then pushes the air through a desiccant rotor, which is made of a desiccant, primarily of a desiccant material. Different manufacturers can use different types of desiccants. You can find maybe silica gel or activated charcoal or molecular sieve. Basically any material which physical ability is to adsorb moisture so that the water molecules physically stick on the surface of that material. That's basically the principle of it. So the air, which is warm and humid, will go through this rotor, and the rotor is made up of this material which will physically adsorb the water molecules. So the water molecules will stick onto the surface of the rotor, and the unit will therefore supply warm dry air as number 4. So dry air, it makes sense because the material itself has physically stuck the water molecules on. Why warm? Well, there's 2 reasons for that. The first one is that there is a physical change of state of the water from a gas into a liquid through the absorption process. So therefore, it will follow the line of enthalpy, which we'll clearly see on the next slide when we talk about psychrometrics. So there's a first heat gain through the change of state of water, but there is also a second heat gain, which is down to the second air path that I was talking about a minute ago, which is shown at the top here as numbers 2 to 3, and it's referred to as the regeneration air path. And what we do here is we draw air usually from outside, and we'll heat that air up to anywhere between 90 to 120 degrees C. Different manufacturers will give you different values depending on the type of material that they're using, etc., etc. But basically, we tend to heat the air up to anywhere between 90 to 120 degrees Celsius. The idea here is that the air at that temperature is although the moisture content physically hasn't changed, as the air heats up, it expands. So the percentage relative humidity at that point, at that temperature, has decreased to around 1 to 2% relative humidity. And this means that as the very hot, very dry air heats the regeneration portion of the desiccant wheel, it physically then has no choice but to absorb the water molecules that were stuck into the rotor and push them out of the rotor into number 3, which is the regeneration air outlet. And that regeneration air outlet must always be ducted to outside, because that's basically how you're getting rid of that moisture, is through pushing the moisture out to outside. So what does it look like on a psychrometric chart? So first of all, the air goes through the desiccant wheel. So it comes from the room as warm and humid, and then goes through the desiccant wheel, where it will supply as number 2. And at that point, like I said, there is a dehumidification. As you can see, there's a clear decrease in moisture content. But there is also a clear increase in a temperature, which we'll talk about in a minute. My apologies. Now, the second part of the desiccant drying section is the regeneration, which is the second air path, which we saw on the previous slide at the top. And the idea here, again, is to heat the air up to normally around 90 to 120 degrees C. Obviously, the psychrometric chart is a bit too small to go that far, but you get the gist. And as the relative humidity at that point is extremely low, then the air is physically able to absorb the water molecules from the rotor and be able to push that moisture out of the rotor. So what does it mean in terms of changes to moisture and temperature? Well, like I said, there is a clear decrease in moisture content between 0.1 and 0.2. That value is typically around 5-6 grams per kilogram. Again, it depends on the specificities of the desiccant dryer that you are using. And as you can see, there is also a large heat gain, a large temperature differential between 0.1 and 0.2. And this is down to, first of all, the physical change of state of the water from a gas into a liquid, which means that we are physically releasing heat energy into the air, which means an increase in temperature. And then there is a second heat gain, which is down to the residual heat left in the rotor from the regeneration process. And that second heat gain is typically around 1.5 to 2 degrees C per gram of moisture removed. So as you can see, two very different technologies, two very different psychrometrics. So what are the main differences other than the principle of operation between the desiccant dryer and the condensing dehumidifiers. Well, that's exactly what we're going to look at next. So in terms of products themselves, first of all, in terms of condensing dehumidifiers, I'm afraid that from outside, there's nothing really too exciting about those units. They're very basic. You know, it's a box. It doesn't look like much from outside. Everything that we saw on the previous slide happens internally. So internally, you will have your full refrigerant circuit. So with your evaporator, your compressor, your condenser, your expansion valve, etc., etc. And then you will have your fan. So from a physical point of view, the air is usually drawn from the side of the unit. As you can see, there is a filter on the air inlet to protect your refrigerant circuit, and then is supplied from the top of the unit. So everything happens internally: the cooling, the reheat, and obviously the fan is there to suck the air in and push it out. So what does that mean in terms of installation? Well, the installation of a condensing dehumidifier is extremely easy. You tend to just put the box on the floor, or you've got wall-mounted dehumidifiers, real wall-mounted. We'll see a few examples in the next slide. You know, you connect power to it, which is either a single phase or a three-phase supply, depending on the capacity of the dehumidifier. And you connect a drain to get rid of the water condensates. But other than that, it's very easy to install. In terms of maintenance requirements, there is a very low spares requirement. It's mainly to do with the air filter on the intake of the unit. Obviously, there are a few visual checks that we recommend to have every 6 months to a year, but those are mainly visual checks. In terms of spares requirements, it is minimal. The one thing to remember, however, with condensing dehumidifiers is we are dealing with a refrigerant, and therefore anyone who needs to do checks or do refill on the refrigerant side of it must be an F-gas certified engineer. So as much as maintenance is fairly easy and straightforward, maintenance on the refrigerant side of this particular type of unit must be carried out by an F-gas engineer. The other thing to bear in mind, and this really depends on the legislation in the United Arab Emirates, but I know that in other countries, as depending on the type of refrigerant used and the quantity of refrigerant inside the unit, you may have mandatory 6 monthly checks or annual checks of the refrigerant circuit as well. So those are things to bear in mind. It's as much as it's fairly easy and straightforward, it has to be carried out by qualified, certified engineers. In terms of power consumption, running costs, the power consumption is actually minimal on condensing dehumidifiers. The main requirements are down to the compressor and the fan itself. Everything else is pretty fairly straightforward. And yeah, in terms of control accuracy, on the outlet of the dehumidifier, because of the compressor constantly being on and off, this will typically give you a control accuracy of plus or minus 10% relative humidity on the outlet of the dehumidifier. Now, obviously, if you have a unit that's in the space with the inertia of the air around and the very low velocity of the air around, as the supply conditions mix with the ambient air, it might actually give you a much more stable reading. But from an operation point of view, you typically get plus or minus 10% RH on the outlet of the condensing dehumidifier. So of installation, as I said, you can have it as a standalone unit, wall mounted. You can have rear wall mounted versions, ceiling mounted, or you can even have a standalone unit with a bit of ductwork, particularly interesting for large areas, just to make sure that the air is, the dry air is distributed correctly across larger spaces effectively. But the ductwork is not always required. It really just depends on how large the area you're trying to deal with effectively. Now with desiccant dryers, again, from the outlets, it doesn't look like much from the outside, sorry. It really is, again, a box and everything is crammed in there. So like I said, you would have a process air fan, you would have your, of course, your filters on the process air inlet and the regeneration air inlet. Sometimes a filter guard. You will have your regeneration air fan with your small heaters, which can be either PTC heaters or could be standard resistive heating types. You know, loads of different things available, but most of it happens internally. So from the outside, doesn't look like much. In terms of maintenance and spares requirements, again, the spares requirement for routine maintenance is very low. You usually typically only look to replace the filters, but obviously an important thing to do in terms of maintenance is just check the rotation of the rotor. So check the belt tensioning, the pulley. And just make sure that everything is working correctly. It doesn't mean that it needs to be changed very regularly, but it's always important to just keep an eye on it, particularly if you see a decrease in the dehumidifier performance. The good thing about servicing and maintaining those units is there's no refrigerant circuit inside, so this can be done by pretty much any qualified engineer with a bit of common sense and the correct tools, effectively. In terms of installation requirements, however, this is slightly different in as much as there is ducting required on the regeneration air outlets. As I explained, on the regeneration air side, we are physically pushing the moisture off the rotor to get rid of it and allow the unit to carry on absorbing moisture. So all that moisture needs to be ducted from the desiccant dryer to outside. So there is a ducting requirement when installing desiccant dryers. The real benefit of this type of unit is that it can operate down to extremely low dew points. I have seen applications where a dew point of -20, -30 degrees C was required, and this can only be achieved by desiccant dryers with the correct amount of design and engineering behind it, but this can be achieved. The downside of this type of unit is that, as explained, we need to heat the air up on the regeneration side to anywhere between 90 to 120 degrees C. Most units will be delivered as standard with electrical heaters, which means that your running costs can actually be quite high. So then, obviously, for larger units, larger air volumes, it might be an idea to try and reduce the running cost of the unit to then look at alternative sources for the heating. So instead of using an electric heater, maybe use gas heating or gas burner or steam heat exchanger to try and reduce the cost of operation of the unit. The other downside of this type of unit is the fact that they do generate a lot of heat through the dehumidification process, and therefore it is quite common to then look at maybe pre-cooling to increase the efficiency of the rotor, or post-cooling coils to offset the heat gain generated by that unit. So both of them will typically, most manufacturers will be able to give you an idea of what the heat gain will be, and then should be able to give you a price for a pre or post cooling coil, depending on the specific site requirements. In terms of a typical installation, like I said, nothing new. This drawing shows 4 ducts connected to this particular unit. The only ducting that is absolutely mandatory with a desiccant dryer is the wet air duct, shown here as number 4. Everything else doesn't necessarily have to be ducted, but can be ducted. And actually, what I will say is, in order to set the correct airflow on the fans, but also to make sure that there is the slight positive pressure inside the units in order to optimize the dehumidification efficiency of the unit, it's always advised to have a damper fitted on both the process air inlet and the reactivation air inlet, just to make sure that the unit is operating down to with optimum conditions effectively. Now, with this said, we've looked at the types of dehumidifiers available, how they work, what are kind of the main features and characteristics. So now let's have a look at how do I size a dehumidification system. Well, first of all, what data do we need in order to calculate the dehumidification requirement? Now, for those of you who have been involved in dehumidification or humidification projects, actually, most of you will be familiar with the type of data that we need in order to do that calculation. So we'll need, of course, to have a feel for the outside air conditions, typically in summertime or in some Asian countries in monsoon periods. Basically, every time where the air temperature is warm and the moisture content is elevated. We'll obviously need to know the room set point. What is it you're trying to achieve? Not only in terms of humidity, but also in terms of temperature. Then we'll need, obviously, those 2 details will then give us, using a psychrometric chart, the moisture differential in kilograms per kilogram. And then, of course, the most important thing of all is how much air do I need to deal with? So, in other words, we need to know the air volume, if there is mechanical cooling happening, or if we are connecting the dehumidifier to the air handling unit, for example, or the room volume if it's a typical space in-room application, effectively. But either way, we need to understand how much air is it that we are trying to dehumidify. And then we'll take also from the psychrometric chart the specific volume in meters cubed per kilogram. And that value is typically taken at room set point because this is the air that you're trying to control this. So therefore, this is the value that you should be taking, really. So we take all those details and we put them in a nice little formula shown here at the bottom, which is basically your moisture differential multiplied by your air volume and divided by your specific volume. And that will give you the capacity required for the dehumidifier from an external load point of view. So it's understanding where the air is coming from and how much moisture do I need to strip off of it. But with dehumidification, there is also an internal load component that we need to be mindful of. And this is to do with, first of all, what's going on? Well, what's going on in the space? So how many people are in the space? You know, a room with 20 people will certainly be a bit more humid than a room with a single person. Now, it also depends on the working intensity of those people. Are they sat down at a desk typing on a computer, or are they physically moving stuff around and sweating a bit more? Now, as much as when questioning your clients, you can turn around and say they will be able to tell you how many people are in the room, but to tell you how much moisture each people generates, they probably won't go that far. So from our point of view as design engineers, what we tend to use are the ASHRAE guidelines in that respect, which is that for a low working intensity of occupants, the moisture gain is 35 grams per hour per person. So low working intensity, 35 grams per hour per person of moisture content, of moisture increase. With medium working intensity, that value goes up to 110 grams per hour per person. And with a high working intensity, so someone running around, moving stuff around, that value goes up to 185 grams per hour per person. So those are ASHRAE recommendations, and those are the values that we tend to use on a daily basis when sizing a dehumidifier. And last but not least, we need to be aware of additional moisture loads in the space. And this is particularly critical when we are dealing with products, hygroscopic products that will physically release moisture as the room ambient relative humidity goes down. It's critical, for example, in a meat drying application. It's important to understand how much meat is in the space, how much weight loss are we trying to achieve, because all that moisture will go into the air and the dehumidifier will need to deal with it. The same with open water surfaces. There was a case, a job we did not that long ago, somewhere up north in Scotland, where the customer had installed a dehumidifier and everything was working well until one day he called the office and said, "Look, my dehumidifier is not maintaining conditions anymore. What's going on?" So we looked at the mechanical aspect of the dehumidifier and everything seemed to be working absolutely fine. So one of our engineers went up to site only to realize that since the design and selection and installation of the system, the customer had installed in this room 2 open top aquariums with hot water. So the hot water was generating moisture into the air that the dehumidifier wasn't sized for and therefore wasn't able to deal with. So again, an internal load that had nothing to do with air coming in or your standard design conditions, but more to do with something that was physically happening in the room and that needed to be taken into consideration. So critical to understand what the application is and where the moisture gains can come from internally as well as externally. And your total dehumidification duty is always your external load plus your internal load. With swimming pools, the sizing is slightly different because, like I said, with swimming pools, it's a case of trying to close the gap between the air vapor pressure and the water vapor pressure. So what we tend to do in swimming pool is tend to look at the room volume, the pool surface area, of course, how big the pool is, and then really focus on the room temperature and the water temperature. And good design practice, particularly for private swimming pools, not so true with larger swimming pools because that's usually a bit more difficult due to the large volumes, but good design practice, particularly for private swimming pools or hotel swimming pools, is to have a room temperature that is at least 2 degrees greater than your water temperature. And this is really to try and balance the water vapor pressure and the room vapor pressure in order to limit the amount of water evaporation in the space. And then obviously the room humidity set point, like I said, usually anywhere between 50 to 60% relative humidity. You don't really need to go below that because you're already at the point where condensation is very unlikely to form because you've reduced the dew point low enough. And the other thing to bear in mind with swimming pools is to do with air circulation, making sure that the dry air is distributed evenly across the whole room, but without causing too much air that it then becomes uncomfortable or a bit windy in there. So good design practice is to have a dehumidifier that supplies between 3 to 7 times the room volume. So in other words, if you have a room volume of 100 cubic meters, then ideally you'd have a dehumidifier that would supply anywhere between 300 cubic meters per hour and 700 cubic meters per hour of air. Those, again, are guidelines. It can vary project to project. It really depends on the size of the area that you're trying to deal with. Larger areas like public swimming pools or Olympic swimming pools are not usually dealt with via dehumidifiers because of the large room volumes. They tend to be dehumidified via air handling unit rather than just dehumidifiers, just because of the sheer amount of air that we need to deal with. Now, last but not least, let's have a quick look at the comparison between desiccant dryers and condensing dehumidifiers. Where do I use one over the other? Well, I think there's a natural split when it comes to choosing one or the other, and it's to do with the room conditions that we are trying to achieve. Now, as we've seen from a principle of operation point of view, condensing dehumidifiers operate with an internal evaporator and rely on the cold surface temperature of the evaporator to remove the moisture. Now, that evaporator typically will have a temperature of anywhere between sort of 10 to 12 degrees C. It really depends on manufacturers and refrigerants and things like that. But basically, they will have a temperature of around 10 to 12 degrees C. So if my target conditions are below 10 degrees C, then we know already that the evaporator won't have the capacity to get cold enough to do dehumidification, and that therefore it's unsuitable. At the same time, 50% RH, if we go much below 50% RH as a target condition, then what will happen is the evaporator will work really, really hard to do a lot of sensible cooling, but at that point it will have very, very little capacity left to do the latent cooling that we need to do to dehumidify. So therefore, I would say that the natural split is anything above 10 degrees C and above 50% relative humidity, I can use condensing or I can use desiccant dryers. Below 10 degrees C and below 50% relative humidity as a target point, I need to use desiccant drying, because desiccant basically can work in any conditions. They're not relying on the temperature of the air or the moisture content of the air to dehumidify. Last but not least, there are a few details as to the main differences between the condensing and the desiccant type units. Obviously, the dehumidification principle we've talked about extensively already. The power consumption, like I said, is very low on the condensing dehumidifiers, mainly the compressor and the fan. With desiccant dryers, you have to take into consideration the heating required on the regeneration side of it. So very high, much higher power consumption. Heat emission to the space, we've seen on Psychrometrics that it's very low with a condensing dehumidifier. It's much higher with a desiccant dryer, simply down again to the technology itself. Ducting required, obviously not necessary with condensing dehumidifiers, always necessary on the regeneration air outlet of a desiccant dryer. However, in terms of achievable relative humidity, down to 50% relative humidity with a condensing dehumidifier, down to potentially 1% relative humidity with a desiccant dryer. Operating temperature ranges, as we can see quite clearly, the desiccant dryer can operate down to much lower dew points and much lower temperatures, whereas a condensing dehumidifier really is limited to the maximum cooling capacity of the evaporator coil. In terms of installation, condensing dehumidifiers can be sometimes mobile. Desiccant dryers, because of the ducting requirements, are typically stationary. In terms of air circulation, obviously each units are available in a multitude of air volumes. So a condensing dehumidifier will probably need a bit more air to improve the efficiency of the evaporator, but that's about it. And in terms of capacity, depending on low temperatures and high temperatures, well, we've already gone through that in details in the previous slides. So yeah, those are basically the main salient points, the main differences the main points that we look at when we try to choose one solution over another. Okay, on that note, yes, Condair do design, manufacturing, commissioning, service, site service, risk assessments, basically any humidification or dehumidification requirements. Please feel free to contact us. I thank you all very much for your time and patience. Does anyone have any questions?
Thank you, Julien, for your very insightful presentation. It has been very technical and instrumental, as you have touched bases on a lot of psychrometric fundamental principles, which is always good to refresh, and for those who don't know, just to learn, and application components. So thank you very much for that. You have quite a lot of questions. I've been reviewing the most relevant ones, and I'm going now to read them, and if you kindly can respond to the question for the audience.
Yes, absolutely.
Right, thank you. So first question that we got is, I think you also covered with one of the latest slides, but perhaps just a quick brief and summary. Which solution is more energy efficient?
Well, from an
probably comparing between the both of the system, the condensing and the desiccant dryer, probably.
Yeah. So from an energy consumption point of view, the best solution is always the condensing dehumidifier, simply because of the low power requirements to the fan and the compressor compared to the power requirements to the heating of the regeneration side on the desiccant dryer. So it's usually more energy efficient to use a condensing dehumidifier. However, it really depends on the application, and more importantly the design the design temperature and humidity that you are trying to achieve.
Thank you, Julien. On this energy node, one question is, we have discussed the desiccant dryer with a preheating element that will actually increase the temperature, so then the moisture absorption can be larger, and this brings also perhaps an additional increase in the cooling, because you need to post-cool later on. When you, I mean, is there any? Can you brief on a relation between energy? Is it like a balance between energy cost and application between the use of this or a similar system without the preheating element? So you don't have to preheat, which consumes energy, and you don't have to post-cool so much. And what kind of moisture ratio or a range of moisture ratio you could be getting between one system and the other?
Right. Okay. I think this is quite an extensive question. So basically, the thing with desiccant dryers is you have to think of the rotor as a towel that you use every morning after your shower. You need the towel to be dry so that you can dry yourself, so that you can absorb the water molecules from your body. So that's the drying part of it. And then the second part is obviously if you want to use your towel again later on that day or the next morning, you need to put your towel on the towel rack or outside where the air is warm in order to get rid of the moisture that's accumulated in the towel, ready to be used again. So in terms of the desiccant dryer and the regeneration requirement, it's exactly the same. It's a case of we need to regenerate that well. We need to allow it to absorb moisture again. And to do that, we need to heat the air up to a certain temperature so that the air is physically dry enough to absorb that moisture accumulated and to get rid of it to outside. So yes, I understand that. Yes, you could potentially reduce your regeneration heating capacity, which will further reduce your post-cooling requirements. But then it becomes a case of where do you draw the line so as to be still efficient from a dehumidification point of view, compared to actually losing too much efficiency because you're not heating the air up enough. Each manufacturers will have a slightly different set of data, depending, like I said, on the type of desiccant material that they're using, depending on the size of the rotor that they're using, depending on the type of airflow that they're using as well. So there's a number of components that are taken into the consideration when designing desiccant dryers, and in order to really optimize the dehumidification whilst also keeping the energy consumption as low as possible. There is, of course, in answer to your exact question, yes, you can reduce the heating power requirements, but you have to be able to accept a loss in efficiency of the rotor and therefore a loss in dehumidification.
Thank you for that, Julien. Thank you for that response. Next question is, can desiccant rotors be used for healthcare application?
Absolutely. Yes, absolutely. In fact, they are vastly used in pharmaceutical industries, but also in we have seen some installed on the fresh air dehumidification to hospitals. Simply to obviously try and reduce the amount of moisture coming from outside, particularly in warm or hot and humid days in the summer. Yeah, there's no reason why not. There is no addition of particles or anything like that from a desiccant dryer to say, okay, it's not, it's not safe or hygienic. There's nothing there to suggest any of that. So yes, I see no problem at all, providing of course you have the cooling the cooling available to offset the heat gain.
Definitely. Thank you for that. Next question we have. Okay, condensing units. Do we have an installation available above false ceiling?
Yes, absolutely. There is a ceiling mounted version which can be installed above full ceiling. We have some units actually installed above a false glass ceiling, actually in the museum somewhere in the UK. So the unit's physically visible, and yeah, no problem at all.
Okay. Next question we have is, any reason why inverter or digital scroll compressors are not used on condensing dryers for better control accuracy?
That is a very good question, and the answer is no particular technical reason that I can think of. A lot of the time is probably to do with the price, actually, of the units. Obviously it's a very competitive market out there, so most manufacturers will elect to go for a cheaper compressor in order to remain as competitive as possible. From a mechanical point of view, I see no reason why you couldn't use a different compressor if you wanted something a bit more accurate.
That's good. Another question is, pre-cooling, post-cooling, do we have DX option or chill water option? I think the question also, you have talked about DX, whether there is also option available with the chill water option.
Yeah. I mean, obviously, different manufacturers will have different options available. I can't talk for all of them, but from what we have seen at Condair, we can supply both DX and chilled water coils as an option.
Thank you. This is another question. I think you touched bases on flow rates per equipment before, but let me just ask this question so you can provide reassurance to this person. Basically, there are filters inside the dehumidifiers, and what is the range of airflow that the dehumidifier can maintain?
There's a very wide range of airflows on condensing dehumidifiers. We typically, our range of products, again, I can only talk about what we do, but we range anywhere between sort of 500 cubic meters per hour to 9,000 cubic meters per hour. On the larger units with desiccant dryers, we can go anywhere between sort of 160 cubic meters per hour to 27,000 cubic meters per hour. So yeah, a very wide range of air volumes available.
Thank you. What about the refrigerant? What refrigerant the condensing units use?
So different manufacturers use different refrigerants. Most manufacturers, including ourselves, use the R410A refrigerant. Still, we understand that it's becoming a potential issue in domestic applications at the moment, and then I think the most of the industry is already looking at alternatives, but at present, from an efficiency point of view and a cost point of view, they still run on R410A.
Okay, there's a question here, probably for the desiccant dryer. External static pressure for ductwork in Pascal that you can install for this type of unit. What is I think the question is, what is the maximum ESP, the external static pressure for the ductwork in Pascal that you can install? Desiccant dryer, larger space problem.
Okay, it depends on the type of fan that you're using, whether it's an AC fan or an EC fan. And it depends on the airflow rates that you're using compared to the maximum airflow of the fan. But typically, with sort of main industrial units, you should expect around anywhere between sort of 200 to 350 pascals available static pressure on the fans. Like I said, it can be increased if you reduce the airflow slightly, or there's so many parameters. But on average, I would say between 200 and 300 pascals should be available.
Okay. A question is on maintenance. What are the maintenance requirements during the use of a desiccant dehumidifier?
Okay. Well, in terms of maintenance, obviously the one item that needs to be replaced regularly are the process air filter and the regeneration air filter. Those are the two items that need to be replaced frequently. In terms of other items, obviously, the rotor, most manufacturers won't necessarily change it. You should expect a good lifetime out of the rotor. So the other things that are likely to not break down but get a bit knackered over time are like I said, the belt assembly. So it's the gear motor, it's the It's the belt pulley. It's the belt tensioning system sometimes, and also, of course, the fans and the heaters. So, like I said, most at the beginning, I would say, for the first 2-3 years, it's usually like at least visual checks. I wouldn't expect to change anything other than the filters for at least 2 to 3 years. After that, then that's when particularly the belt assembly starts getting a bit tired, particularly if the desiccant dryer has been running very hard.
Thank you for that, Julien. It's another bunch of questions. I'm going to be selecting. Okay, for sizing airflow required for swimming pools, do we only look at the pool area and moisture release from the pool, or should we also look at the moisture generated by the people? I think you already touched bases on this before, but if you want to just wrap up for this person.
Sorry, did you say the moisture generated by people?
Yes, I'll repeat the question. Yeah,
okay.
When sizing the airflow required for the swimming pool, do we only look at the pool area and the moisture, probably the activity factor, the moisture released by the pool, or we also look at the moisture generated by the people?
Okay. No, we tend to look at the moisture generated by the pool itself. What we find is that the moisture generated by people has a very, very low incidence compared to the moisture release, the moisture evaporation from the pool itself. You could take it into consideration, absolutely. And in fact, if you want to dot the I's and cross the T's, by all means, allow for moisture gain from people. But from our experience, by the time you've calculated the moisture release from the pool and you've taken into consideration how the pool operates and things like that, then you tend to have enough spare capacity in the dehumidifier itself to allow for moisture gain from other people effectively.
There is a question on what about the life duration of the equipment? So I think it's a little bit on touching on life expectancy from a specification point of view. Yeah.
Of course. I mean, as with any other mechanical equipment, it depends on how hard the system is running and the number of hours of operation per year. But you would expect at least a good 8 to 10 years out of any dehumidification system that you're using. At least 8 to 10 years, without a doubt. Anything below that is just, it doesn't sound right to me, to be honest.
Excellent. Another question is, how do we calculate the capacity of the heater of the desiccant dehumidifier? I think if you can just give a quick brief, no need to enter in.
So, yeah, I mean, as a design engineer, personally, I would contact the manufacturer and say, this is how much dehumidification I need to do, and let them size it up for you. But effectively, if you wanted to get a feel for how much power consumption you might need, then what you should do is basically take a minimum air-on temperature of 90 degrees C. Assume that you start from, I don't know, sort of 10-15 degrees C air-on. So that gives you a delta T of 80 degrees C. So what you do is you take your 80 degrees C, you multiply it by your standard density, which is 1.207, and then multiply it by an airflow. Now that airflow should be normally, as a guideline, don't quote me, it's not always the case, but as a rough estimate, your regeneration airflow should be around a third of your total airflow. So say you need a dehumidifier airflow of 1,000 cubic meters. Well, you take a regeneration airflow around 300 cubic. So 300 cubic meters per hour, which you divide by 3,600 to get to your meters cubed per second, multiplied by your delta T, which is at least 80 degrees C, multiplied by your density, and that gives you a power consumption in kilowatts. Mm-hmm. So again, it's not, you know, by all means, don't rely on yourself to design the heating capacity of a desiccant dryer. But if you wanted a rough guide on how to estimate it, that would be my starting point.
Thank you for that. That was very precise. Okay, there are a number of questions here. I'm gonna start to cut it short, I think, because we are running out of time. With desiccant type, what is the lowest dew point which can be achieved?
I would say with the absolute lowest dew point that I've achieved so far in my dehumidification career was around minus 38 degrees C. But then it becomes a very, application specific product. I would say that it's not going to be your standard desiccant dryer that's off the shelf effectively. In terms of limitations with a standard unit, I would expect I don't know, about minus 20 degrees C would be easily achievable with some sort of standard unit.
Mm-hmm. Give that. Okay, let me see if there is something here. Okay, it's a question. Key factors to consider when designing for a swimming pool dehumidifier if there is an existing AHU in the swimming pool area.
Yeah.
So what are the key factors to consider when designing? I'm not sure if the question is too clear. For you?
Obviously, if the the AHU will very likely pre-treat the air to at least dehumidify the fresh air intake of it. If it doesn't, for any reason, then obviously you'll need to consider the outside air volume as a source of moisture ingress into the space. But other than that, like I said, it's really mainly to do with room volume, water surface area, water temperature, room temperature, and like I said, if the AHU is not sized to handle the fresh air ingress from a moisture content point of view, then you'll need to take this into consideration as well.
Okay, thank you. I think, Julien, thank you very much for the Q&A session. I'm going to have to leave it here, being cognizant of the time limitation. Okay. For the audience, we have in the screen Julien's slide where his contact details, telephone numbers, and email are displayed. So please feel free to raise any further questions that you may have in future or was not raised today. And Julien will be more than happy to respond to those.
Absolutely, absolutely.
I think that's it for today. Thank you very much to the audience for attending to this session. I hope you have enjoyed this webinar and you have learned quite a lot from the knowledge sharing that Julien has been kind enough to share with us today. And Julien, once more, thank you very much for your insightful and very instrumental presentation given.
Thank you thank you very much, everyone, and thank you, Alejandro, for giving me this opportunity.
Thanks to you, Julien. Please follow us on social media through our LinkedIn and Twitter accounts. You can see also our website as displayed in the screen, and feel free to reach us out on our email ID, uae@cibse.org. Have a nice evening, and looking forward to seeing you in our next CIBSE UAE webinar.
Thank you, everyone.
Thank you.